You have probably stood in front of a building on a hot summer day and felt the heat radiating off the walls. But here is something nobody tells you. That heat is not just warming the surface, it is physically moving it. And the most famous structure on Earth moves so much because of it that engineers had to design the whole thing around that movement. The Eiffel Tower grows 18 centimeters every summer. Gustave Eiffel planned that in 1887. Here is exactly how. Before we get into why, you need to feel what we are actually talking about. The Eiffel Tower stands 330 meters tall, including its antenna. That is taller than a 90-story skyscraper. It weighs approximately 10,100 metric tons. To put that in perspective, that is roughly the weight of 1,400 adult elephants stacked on top of each other. It was built between 1887 and 1889 using 18,038 individual iron pieces held together by 2.5 million rivets. At the time of its completion, it was the tallest man-made structure on Earth. It held that record for 41 years. And every single one of those 18,038 iron pieces does something that Gustave Eiffel knew about, planned for, and built into the design over 130 years ago. Here is what most people assume. Steel and iron are hard, they are solid, they are rigid. You build something out of metal and it stays exactly where you put it. That assumption makes complete sense. Drop a piece of iron on the floor and it does not bend. Hit it with a hammer and it does not stretch. Leave it outside and it does not grow. But here is what your intuition is missing. Solids expand when they are heated. Every solid, every material, every metal structure ever built. You have actually seen this your entire life without realizing it. Look at a railway track. There are small gaps between the sections of rail. Those gaps are not a mistake. They are not poor engineering. They are there deliberately because the engineers knew the metal would expand in summer and needed somewhere to go. Look at a bridge, any large bridge. There are expansion joints built into the road surface, gaps filled with flexible material that allow the bridge to grow and shrink with the seasons without cracking. The Eiffel Tower is no different, except the numbers are much more dramatic. Here is what is actually happening inside that iron structure every summer. When temperature increases, the atoms inside a solid material vibrate faster. As they vibrate faster, they push against each other with more force. That force pushes them slightly further apart. The material gets very slightly larger in every direction. This is called thermal expansion, and for iron, the expansion is predictable, measurable, and consistent. Iron expands by approximately 0.000012 meters for every meter of length, for every degree Celsius of temperature increase. That number is called the coefficient of thermal expansion. Now apply that to the Eiffel Tower. The tower is 300 meters of iron structure, ignoring the antenna. Paris temperatures between winter and summer can vary by as much as 40 degrees Celsius. Run the calculation, and you get approximately 0.000012 multiplied by 300 multiplied by 40. The answer is 0.144 meters, almost 15 centimeters. On the hottest days compared to the coldest days, the Eiffel Tower grows by up to 18 centimeters. When you account for solar heating of the dark iron surface, which absorbs sunlight and heats the metal beyond the air temperature. That is not a flaw. That is physics working exactly as it should. And Gustave Eiffel knew this in 1887, before a single rivet was driven. But here is the part that genuinely surprises people. The expansion does not happen evenly across the whole structure, and that creates something nobody expects. The Eiffel Tower does not just get taller in summer, it also leans. On a sunny day, the side of the tower facing the sun heats up faster than the side in shadow. The sun-facing iron expands more. The shaded iron expands less. And when one side of a structure grows and the other does not, the whole thing bends slightly away from the sun. The tower can lean by up to 18 centimeters away from the sun on a hot, clear day. This sounds alarming. It is not. Gustave Eiffel designed the structure to handle exactly this. The four curved legs of the tower and the lattice iron framework are specifically shaped to distribute these forces safely across the entire structure. But it raises a deeper question. If the tower moves this much, how does anything attached to it stay in place? The answer is in something called the thermal expansion joint. Every large structure that experiences significant temperature change has them. They are deliberate breaks in the material, gaps filled with flexible connectors that allow sections to move independently, without transferring destructive stress to the rest of the structure. On the Eiffel Tower, the design itself acts as the expansion system. The lattice framework, those diagonal iron beams crossing back and forth, does not fight the expansion, it accommodates it. The gaps between iron elements allow each piece to move slightly, without cracking the joints or buckling the structure. This is the engineering insight that made the Eiffel Tower possible. Not the height, not the weight, the understanding that a rigid structure fighting thermal expansion will eventually destroy itself. A flexible structure that works with thermal expansion will stand for centuries. And here is where it gets genuinely remarkable. Because this principle is not just in famous towers, it is in almost every structure around you, and once you see it, you cannot unsee it. Think about the road you drove on this morning. Look carefully at the surface next time, and you will notice lines cut across the road at regular intervals. Those are control joints, deliberate weak points that allow the concrete to crack in a straight, predictable line, rather than randomly across the surface as it expands and contracts. Think about the railway tracks outside your city. Those small gaps between rail sections exist for the same reason. On early railways, before engineers fully understood thermal expansion, rails were sometimes laid without gaps in warm weather. When winter came and the metal contracted, sections of track pulled apart at the joints. When summer came and rails expanded with nowhere to go, they buckled sideways. Trains derailed. People died. The gaps exist because of those lessons. Think about large glass windows in skyscrapers. The glass is not fixed rigidly into the frame. It sits in a flexible seal that allows it to expand in summer without shattering against the rigid frame. Think about the Golden Gate Bridge in San Francisco. Its total length changes by approximately 1 meter between the coldest winter day and the hottest summer day. Expansion joints built into the road surface absorb that movement silently. Every single year, every large structure on Earth is moving, constantly, silently, invisibly. The only question is whether the engineers designed it to move safely, or whether the structure will eventually force its own movement in a far more destructive way. Gustave Eiffel understood this in an era before computers, before modern materials, science, before the engineering tools we now take for granted. He calculated the thermal behavior of his structure by hand, using the known properties of wrought iron and the expected temperature range of Paris. He designed the lattice framework not just for aesthetic reasons, and not just for wind resistance, which was the main engineering challenge of the time, but to distribute thermal stresses safely across thousands of individual members. When the tower was first proposed in 1884, it was widely mocked. Artists and intellectuals signed a petition calling it an eyesore. Critics called it the iron disgrace of Paris. The mathematician who reviewed the initial designs predicted it would collapse within weeks. It has now been standing for 136 years. It has survived 2 world wars, decades of millions of visitors climbing its stairs and elevators, and approximately 13,000 summer and winter cycles of expansion and contraction. Every summer it grows, every winter it shrinks, every hot sunny afternoon it leans slightly away from the sun, and every time, it returns to exactly where it started. Here's the connection that most people never make. The same thermal expansion principle that moves the Eiffel Tower 18 centimeters is the reason your car engine needs to warm up before it works efficiently. The metal components inside a cold engine are at their resting size. As the engine heats up, those components expand to their working size, the gaps between moving parts close to their design tolerances, and the engine runs as it was built to run. It is the reason your bicycle tire pressure drops in winter and rises in summer. The air inside contracts when cold and expands when hot. It is the reason the Liberty Bell cracked. Thermal stress from uneven expansion during a cold winter day in 1846 created a fracture that spread through the bell and has never been repaired. Every material, every structure, every object around you is in a constant slow conversation with temperature, expanding and contracting, growing and shrinking, moving in ways too small to see, but large enough to crack concrete, buckle railway tracks, and tilt a 10,000-ton iron tower 18 centimeters toward the sky. So the next time you see a photo of the Eiffel Tower, know that what you are looking at is not a frozen monument. It is a living structure, breathing with the seasons, expanding in the summer heat, contracting in the winter cold, leaning toward the shade on sunny afternoons, and returning to center as the temperature drops. Gustave Eiffel did not just build a tower, he built a structure that understood physics well enough to survive it for over a century. And if the Eiffel Tower surprised you, wait until you find out why the Burj Khalifa was designed with a specific flaw built directly into its structure. One that engineers say is the only reason it is still standing. Subscribe so you do not miss it.